So today's class is basically the second class of the previous class, and in the previous class we have discussed about the discrete distribution and the continuous distributions. So let us define the mathematical expectation today. First, what is mathematical expectation? So let x be a random variable, let the distribution of x be discrete, and let the spectrum of x consist of the points x minus 2, x minus 1, x naught, x1, x2, etc. and following this in equation, and probability of x is equal to xi is equal to fi. This is the probability mass function as we know from the discrete distribution, and gx is a continuous function. We define the mathematical expectation of the function gx for any discrete random variable x to be denoted by expectation of gx. This is the notation, is equal to summation I equal to minus infinity to infinity gxi fi. Discrete scenario, fi is the PMF, probability mass function, because in the discrete case we use the term mass, and this is the definition of the expectation of gx. It's simply summation gxi fi, provided the series converges absolutely. Now let us define the expectation for a continuous random variable. Let x be a random variable and the distribution of x be continuous. If x be its density function, PDA, probability density function. In the case of discrete we use the term probability mass function. In the case of continuous we use the term probability density function. And gx is again a continuous function, so we define the mathematical expectation of gx is defined by, in that case we use the summation symbol. In this case is the continuous case, we use the integration symbol, and is defined by this integration. Expectation of gx is equal to minus infinity to infinity gx fx dx, provided the integral converges absolutely. So this is the definition of expectation in the discrete case and in the continuous case. Let us define the mean. What is mean of the distribution? Let x be a random variable. The mean of x is nothing but the expectation of x. So mean is your expectation of x. So mean is defined by, so in the discrete case it would be I into fi summation. In the discrete case if you take I into fi. So in the continuous case it will be transformed into integration. So what is that? Integration minus infinity to infinity x fx. X fx dx. So that is the mean for the continuous distribution. What are the moments? We define the moments. Let x be a random variable and k be a non-negative integer. Then kth moment of x about a fixed point a is defined to be expectation of x minus a whole to the power k about a fixed point a. And what is kth moment of x? Kth moment of x is simply alpha k equal to expectation of x to the power k. This is raw moment actually. And kth central moment is always about the mean. So this is denoted by x minus f m whole to the power k. So there are two types of moment. One is a raw moment, one is a central moment. If we want a moment about a point, then we can define this, and expectation is already defined above. Now we define what is variance. Variance is the second central moment mu2. So naturally variance of x is denoted by expectation of x minus m whole square. And what is standard deviation? Is a square root of variance, positive square root of variance, and where mean is expectation of x. So variance is nothing but your second central moment. Now let us define a few important definitions, very important in probability. One is a moment generating function. What is moment generating function? The moment generating function of a random variable x is a function of a real variable t denoted by psi t and defined by psi t is equal to expectation of tx, expectation of e to the power tx, not expectation of tx, expectation of e to the power tx. So you know that exponential function, series of the exponential function, we can easily find out the expectation of e to the power tx. So this is very useful. We can find out the moment generating function for different distribution, discrete, continuous, so on. Next we define the characteristic function of a probability distribution. The characteristic function of a random variable x is the function of a real variable t denoted by chi t, and it is defined by chi t is equal to expectation of e to the power itx. So in that case, moment generating function, there was no I, but in this case you have e to the power itx. I is the complex number. I is root over minus 1 as we denoted in the complex number. Next we prove an important theorem for finding the variance, sigma square theorem. Sigma square is equal to alpha 2 minus m square, or that is equal to expectation of x minus m, expectation of x into x minus 1, m into m minus 1. So this is the sigma square. Let us prove that. Let x be a random variable. We know that sigma square is second central moment. So expectation of x minus m whole square. We expand it. We split up this, and we know expectation of 2m is a constant. So only 2m into expectation of x. Again expectation of x is m. So naturally, if you substitute, we will get the result. Now what is sigma square? Again we can write sigma square as this expansion, and x square as x into x minus 1. So balancing that extra x by plus x, and again taking common and writing this and splitting off, we get this. Again writing expectation of x as m, and finally we arrive this relation. This relation is very useful while finding the variance. Now next question, find the mean and variance of a binomial distribution. Let us find out the mean and variance of a binomial distribution. Let x be a binomial NP variant, and that is x follows binomial NP distribution. Mean, therefore mean is equal to, we can write summation I equal to 0 to n. We know that the spectral point takes the points from 0 to n, so that is equal to, from the previous definition, I into fi. In this case fi is given by nci p to the power I 1 minus p whole to the power n minus I. So I equal to summation I equal to 1 to n I into this nci, we can write this p to the power I 1 minus p whole to the power n minus I, and the first term is 0, so we take the summation I equal to 1 to n. Now this I and this I we can simplify, and this I we can write I into n I minus 1 factorial I minus 1, I will get cancelled, and since n, we can write n into n minus 1 factorial n minus 1. We need to write this in a form, so we take np as common, so that p power of p will be p to the power I minus 1, and here we have n minus factorial n minus 1, and we write the denominator as n minus 1 minus of I minus 1. So all the terms, you look at all the terms are I minus 1. Power is I minus 1. Here we have I minus 1, and here we have I minus 1. So we can replace I by j, I minus 1 by j. So the summation will be from j equal to 0 to n minus 1, and naturally we have factorial n minus 1. This is j, I minus 1 is replaced by j, n minus 1 minus j, p to the power j, 1 minus I, j minus 1. So we have np, rewrite this series as np summation j equal to 0 to n minus 1, n minus 1 cj, pj, 1 minus p whole to the power n minus j minus 1. So we have p plus 1 minus p n minus 1 whole to the power n minus 1 binomial series. So we have np. So mean of the binomial distribution is np, proved. Now we will prove variance, find out the variance. So before that we have to calculate exponential of expectation of x to the power expectation of x into x minus 1. So again, as a previous case, we know that expectation of is this from the definition I into I minus 1 in CIP. Again the first two terms will be 0, so we write the summation from I equal to 2 to n I minus 1. So in this case we have to write I minus 2, because these two term will be cancelled. So we are writing I minus 2 factorial n minus I minus 2. Again we are taking n into n minus 1 into p square, as we want p I minus 2 in the power. So we have I minus 2, we are writing I minus 2 in the same way in the denominator, and finally we write replacing I minus 2 by j. So j equal to 0 to n minus 2, and finally we writing the binomial as in this form, and we have the binomial series as 1 minus p plus p whole to the power n minus 2. So we have n into n minus 1 into p square. This is the value of the expectation of x into x minus 1. So we know this relation from the previous theorem. We will substitute the value of m is np. This is also np, and this already find out n into n minus 1 p square. We will calculate and we will get np into 1 minus p, and writing 1 minus p as q, we will get the final result 1 npq, where p is the success and q is the failure of the binomial distribution. So this is the variance of the binomial distribution, and standard deviation will be root over npq. Next we will find out mean and variance of the Poisson mu distribution. Let x be a Poisson mu variate. So expectation of x is I equal to 0, summation I equal to 0 to infinity I into, from the definition, I into the fi. Fi is given by, for the Poisson distribution, fi is given by e to the power minus mu I to the power I factorial I, and mu is the only parameter of the Poisson distribution. So e to the power, taking e to the power minus mu into mu common, we write this. This is also the writing I minus 1, I equal to 1 to infinity. So I minus 1 we are writing, replacing by j. So summation j equal to 0 to infinity mu to the power j factorial j. This is nothing but your exponential series. So this is u to the power minus mu. So we have mu only. So mean of the exponential distribution is Poisson distribution is mu. Again we are going to find out exponential expectation of x into x minus 1 as in the previous same calculations. We are writing I minus 2 factorial I minus 2, again writing this series, replacing j by I minus 2. In the same way, writing the exponential, we have mu square. Finally we will substitute in this relation and we will get variance as mu. So Poisson distribution is that distribution whose mean and variance is same, and that is given by mu. So today we finish our class here, and this is our about our some mean and variance of some discrete distribution, definition of mean for continuous case and in discrete case. So thank you all.